What is power factor correction in grid-tied systems? Imagine your electrical system as a team trying to work smoothly together. Sometimes, the team struggles because some members are not pulling their weight. That's what happens when reactive power causes inefficiencies in electrical systems connected to the grid. Power factor correction is like giving the team the right tools to work better together. In simple terms, power factor is a number between 0 and 1 that shows how effectively electrical power is being used. A power factor of 1 means all the power is being used for useful work, like lighting or running appliances. But when the power factor drops below 1, it means some of the power is wasted on reactive power. Reactive power does not do any useful work but still causes current to flow, which can lead to problems. In grid-tied renewable energy systems, such as solar panels connected to the utility grid, reactive power is often generated by power electronic devices and inductive loads like motors. These loads cause the current to lag behind the voltage, which lowers the power factor. When the power factor is low, the system becomes less efficient, and more current is needed to deliver the same amount of useful power. This extra current can cause increased losses in cables and transformers, and it can even lead to voltage drops that affect the quality of power supplied. Power factor correction helps fix this issue by adding devices that supply reactive power to the system. These devices are usually capacitor banks or advanced power electronic units that produce leading reactive power. By doing this, they offset the lagging reactive power caused by inductive loads. The goal is to bring the power factor closer to 1, which means more of the electrical power is used effectively. In practical terms, capacitor banks are connected in parallel with the load, either in single-phase or three-phase systems. In larger systems, such as industrial renewable installations, these capacitors are connected in star or delta configurations to balance the reactive power across all phases. Automatic power factor correction units can switch capacitors on or off depending on the load, making the system more dynamic and responsive. Some systems also use synchronous condensers or modern power electronic devices like static VAR compensators or StatComs to provide reactive power support quickly and efficiently. The benefits of power factor correction in renewable energy systems are significant. It reduces the amount of current drawn from the grid, which lowers losses and improves overall efficiency. It also increases the capacity of the system by freeing up apparent power, allowing more energy to be generated or consumed without upgrading infrastructure. Better power quality and voltage stability are additional advantages, helping to prevent equipment damage and reduce utility costs. However, there are some challenges. Improperly designed capacitor banks can cause voltage fluctuations or harmonic distortion. Reactive power compensation needs to be carefully controlled because renewable energy generation can fluctuate with weather conditions and time of day. Many grid operators now requiring renewable energy systems to maintain a certain power factor range to keep the grid stable and reliable. In summary, power factor correction in grid-tied systems is a key part of making renewable energy systems more efficient and reliable. It involves adding devices that supply or absorb reactive power to keep current and voltage in sync. This process helps reduce losses, improve power quality, and support the stability of the electrical grid as more renewable sources come online.